This is how you can analyze the data that you collected from the refraction experiment, where you shown an array of light to the flat side of a cylindrical lens, and measured the refraction angle, the incident angle, and the refraction angle. So the first thing you need to do is to set up a spreadsheet using Microsoft Office, Microsoft Excel, I guess I should say, because other sorts of ways of doing it, I'm not sure you can do trend line analysis. So go ahead and use Excel because we know it works. So the headers that you want, there are 6 of them, that you want the angle, incident angle, that's what the subscript I is, right here, and you want to record the data that you collected in degrees because that's how you collected it, and then the subscript R is the refracted angle, again in degrees, and so you will go ahead and put those headers in and put in the data you collected. This is just some sample data. And you don't have to get fancy using the thetas and the subscripts and that kind of stuff. I just did because I can. Now you might remember from Physics 111 that in the world of physics that frequently, especially when you're talking about rotation, that using radians rather than degrees is preferable. It also turns out that Excel thinks in radians, calculates in radians rather than degrees, and so we're going to need to convert our degree measurements into radians, and I'll show you how to do that in a moment. So you'll have columns for where you're going to calculate the radian angles, the angles in radians for both the incident and the refracted. And then the last thing that we're going to do is to take the sine of that angle, and that's why we have to put it into radians, because Excel will only take the sine of radian measurements rather than degrees. Now, one other little nuance here, you'll notice that for the first 4 columns, the order was incident first, refracted second, incident refracted. Here I have them reversed, and that just is to make the graphing, the charting that we're going to do a little bit easier. So what I'd like you to do at this point in time is to pause this screencast and go ahead and set up your Excel spreadsheet. And once you have your Excel spreadsheet that looks like this, go ahead and come on back here. Okay? See you in a minute. Welcome back. Now what we need to do is use Excel's calculation abilities to convert from degrees to radians. And so what you need to know is what is the conversion factor, and you know that there are 2 pi radians in 360 degrees, or pi radians in 180 degrees, or pi over 2 radians in 90 degrees, etc. The easiest way to probably do it is just to remember that there are pi radians in 180 degrees. And so we're going to go ahead and do an equation here. So we click on the cell, type equals, and then we're going to take the angle in degrees. So I'm going to click on that cell. I'm going to multiply it by pi, and that's probably sufficient for us. And then, not multiply, then I'm going to divide that by 180. And when I do that, lo and behold, I get 0. Now, one of the beauties of Excel is that you can do multiple things. Said a better way, that you can use Excel to do multiple calculations based on the equation you enter. What I'm going to do is I'm going to select this cell that has the equation in it. Go to the bottom right hand corner. You notice how the cursor changes from a fat plus sign to a skinny plus sign. I'm going to drag it to the right, and that's going to go ahead and copy that equation and actually it pays attention to the fact that I've slid over one cell, so now it is using this B column to make the decalculations. Now again, with these two highlighted, if I go to the bottom right hand corner and drag down, it does all of those calculations for us by copying the equations and then taking the appropriate data and then moving forward from there. So that's pretty slick. I hope you would agree. Now we're going to go ahead and enter another equation where we're going to take the sine of the angles in radians. And so we start with equals, and then sine is sin, and open parenthesis. And remember, what I'm doing is doing the refracted ray first, so that's this in the D column. And then that's going to be it. I'm not going to copy that over because then it would be confused as to which angle I want. So I'm going to put another equation where I say the sine, and then now since it's the incident that I want, I'm going to click on that cell. Now that I have the proper equations, I can go ahead and copy those down. And there I have it. And so the final thing, well, not final thing, the next thing I want to do is to go ahead and to make a chart. Oops, don't do that. Let me just highlight the signs, and then I'm going to go to the insert menu, which you can't see from the screencast, but you know where it is. It's up above, and I'm going to insert a chart. And frequently in physics, when we do charting, the sort of charts that we create are ones that are called scatter. And it doesn't really matter, but that's the one I'm going to choose. And what you see here is a fairly straight line, which is a pretty cool thing because it should be. And so what I want to do at this point in time is to have the cursor over one of the data points, hold down, I think it's the command key in a PC or the control key on a Mac. And what I want to do is add trend line. And this is the sort of thing that I don't think you can do with a Google spreadsheet or numbers if you're using a Mac. But what I want is a linear regression because I want to know what the slope of that line is. And so I'm going to click on options, and I am going to ask it to display the equation on the chart, and then I generally do the display R squared value on the chart because that's a measure of how good of a fit it is, where R squared should be as close to 1 as possible. And so if we click OK, that what you're going to find is that the slope of this line, because this is in the slope-intercept form, this is y equals mx plus b, and so m, the slope of this, is a unitless number that's 1.5, and r squared is really, really close to 1, so this is a really good fit. So you want to go through this process with your data and see what you get. And when you're finished with that, you want to look up something called Snell's law and see how that applies to what you've just done here. And then go ahead and look up the index of refraction for acrylic plastic and see how that corresponds to the slope of this line, and maybe you'll have an aha. Hope you enjoyed yourself.